Hello students, good day all. Today we are going to see the continuation of properties of fluids. In that, Torricelli's law, that is the measure of outflow of a liquid, Ventimeter, and the application of Bernoulli's theorem. One by one, let us see students. Yes students, speed of efflux, Torricelli's law. See, this we are going to learn through Torricelli's method. Efflux, which means outflow of a liquid. How the substance outflow through this diagrammatical expression we can see. See the diagram. Now you can see the diagram, the tank which is containing a liquid of density rho with a small hole on the outside of the height h1. See, so this is the height h1, we can take it, and let y2 is the height of the liquid surface from the bottom. This y2 we have taken from the bottom to end, right? And we have taken the pressure P, air pressure, which is P we have taken the above the liquid. If A1 and A2 are the cross section, we have taken two cross sectional area, that is A1 and A2. This we have taken above, which is P, A1, A2, which are the cross sectional area of the liquid. So now we have taken the side wall of the tank, V1, V2 are the liquid velocities at point 1 and point 2. So we have taken, this is point 1 and this is point 2. Okay, these are all the two velocities we have taken. So this is V2, velocity 2, right? Now, as per the Torricelli's law, now the principle of continuity or the equation of continuity we have seen through Bernoulli's theorem. So from the Bernoulli's theorem, we can get that A1 V1 which is equal to A2 V2. So we want to know about this velocity 2. So V2 which is equal to A1, area 1 by area 2 into V1. Okay, now you have to know about as A2 is greater than A1. So the liquid may be taken as the rest at the top, is it right? So that the velocity 2 here at the rest, if suppose here the liquid at rest, then velocity 2, it is approximately equivalent to 0. Is that right? So we are applying Bernoulli's equation. We will get pressure PA plus half rho V1 square plus rho GH or rho G, this Y1 you have to take, the height 1. Okay, that is equal to rho plus, we can write here P, that is pressure. You are comparing the part 1 and part 2. So that we have written here part 1, that is for the this hole and this outflow and the area of which is liquid at rest. So that PA plus half rho V1 square plus rho G Y1 which is equal to P plus rho G Y2, or we can write this as half rho V1 square which is equal to rho G Y2 minus Y1 plus P1 minus PA. Okay, now we will write Y2 minus Y1 which is equal to H, height. So that half rho V1 square which is equal to rho GH plus P minus PA. Okay, now we'll see the value for V1 which is equal to, we will get 2GH plus 2 into P minus PA by rho. So this is the value for that V1 for the outflow. Speed of efflux which is there in the outflow in the velocity V1. Got it children? Yes. Ventimeter. So actually this is the device to measure the rate of flow of a liquid through a pipe. Actually, this is one of application of Bernoulli's principle. We can call Venturimeter, which means flow meter or Venturimeter, right? So the Venturimeter is the device to measure the rate of flow of a liquid through a pipe. See the construction, students. See the diagram. This shows that it consists of actually a horizontal tube which having a wider opening of cross section A1 and narrow opening of cross section A2, right? And these are the two regions of the horizontal tube are connected to the manometer, which is containing the liquid of the rho m density of the liquid it is containing. So this is the setup or the diagrammatical representation of the Venturimeter. How it is working? See, you can take the liquid velocity of V1, which you are seeing here, is the liquid, the velocity of V1 and V2 at the wider and the narrow portions. V1 which is at the wider and V2 which is at the narrow portion which is there, the velocities, two velocities. You can take P1 and P2 or the pressures, the pressure of the liquid at this region. This is for the velocity 1, this is the pressure, and P2 which is pressure 2. Right. So by the equation of continuity, you know that very well. Equation of continuity, what is that? A1 V1 which is equal to A2 V2. So this is the equation of continuity. Or we can write this equation as A1 by A2 which is equal to V1 by V2. Can we write? This format is equivalent to this one. Okay, this is equation of continuity, that is from the Bernoulli's principle we have taken. Now, if the liquid has the density rho and is flowing horizontally, so that we can take this from the Bernoulli's equation, P1 plus half rho V1 square which is equal to P2 plus half rho V2 square, right? Here you can write this, rearrange P1 minus P2 which is equal to half into rho V2 square minus V1 square. That is equal to, we can write half rho V1 square, V2 square minus V1 square, sorry, by V1 square minus 1. Can we write in this format? Okay. So, half rho V1 square, this we can write it as half rho V1 square into A1 square by A2 square minus 1. Because we can take it here V1 by V2, or we can write as per this V2 by V1 which is equal to A1 by A2. Got it? So this is come from this part, right? Now half rho V1 square into, we can write this A1 square minus A2 square whole divided by A2 square, right? Now we can write for P1 minus P2 which is equal to what? H rho G. H rho G. Here we have to take here rho m density. So rho m we can take. Or, see, as we know that H rho G or H rho m G which is equal to half rho V1 square into A1 square minus A2 square whole divided by A2 square. From this, we can write, V1 value, V1 which is equal to root of, by simplifying this, we will get V1 which is equal to V1 square, we can get, by simplified manner I will write V1 which is equal to root of 2h rho mg whole divided by rho into A2 square, right? Yes, whole divided by A1 square minus A2 square. Or we can write Q value. We need Q value. So Q which is equal to what? A1 V1. That we can write it as A1 A2 into the V1 value is what? Root of 2h rho mg whole divided by rho into A1 square minus A2 square. So this is the value for we are getting through the Ventimeter. So the Q value, we can say that that is the volume of the liquid flowing out per second. Okay students, see this is the diagram of atomizer. This helps to spray the liquid. Actually this is working on the principle of Bernoulli's theorem. See the Bernoulli's theorem principle helps to work the atomizer. See the diagram children, the essential part of an atomizer, saying that is the rubber balloon and the spray. Through that pressure too, you are seeing that B part, through the B part it is moving, spray. How it is working? The spray, how it is working we'll see. When the rubber balloon is pressed, the air which is rushes out the horizontal tube B and it is decreasing the pressure to P2, which is less than the atmospheric pressure P1. Right, it is in the container. As a result, you may see that the liquid raises up in the vertical tube A. So when it collides with the high speed air in the tube B, it breaks up into fine spray. So in this way only the atomizer is working based on the principle of Bernoulli's theorem. See children, this is the next Bernoulli's principle of application. It's a curved path of a spinning ball. We can say it's a Magnus effect. When the ball which spins about the axis of perpendicular to its horizontal motion, it carries with itself an air of layer due to the viscous drag. The streamlines which around it are in the form of concentric circles. You may seeing on this first diagram A shows that the streamlines around it are in the form of concentric circles, right? So when the ball moves forward with the velocity v, then the air ahead of the ball rushes backward with the velocity v because it helps to fill the space, the lift empty by the ball. So thus the streamline in air due to translatory motion of the ball are shown in the diagram B. See that? So this, the arrowed part which shows the velocity v that helps to fill the space left empty by the ball. And see the diagram C, this, the layer above the ball which moves in the direction opposite to the spinning ball. So the resultant velocity, see the resultant velocity which decreases, and also you may see that because of the velocity, the resultant velocity getting decreases, the pressure increases in accordance with the Bernoulli's principle. So the layer below the ball moves in the direction of spin. The resultant velocity increases, hence the pressure decreases. Due to the difference of the pressure on the two sides of ball, the ball curves downwards in the direction of spin. So by this way only the ball is throwing and given a spin, then the path of the ball is curved more than in a usual spin of the free ball. So this is what the reason behind the curved path of a spinning ball. So another example, the basis of Bernoulli's principle, lift of an aircraft wing. So we can say that aerofoil, see the diagram children, The aerofoil is, we can say, the name which is given to a solid object that is shaped to provide an upward vertical force as it moves horizontally through the air. So this upward force, that is the dynamic lift we can call, that makes the aeroplanes fly. See the diagram. So this cross section of the wing of an aeroplane that look like an aerofoil. The wing is so designed because of at the upper surface is moved, it's more curved than the lower surface. You may notice that, right? So the front edge is broader than the rear edge actually. So as the aircraft moves, the air moves faster over the upper surface of the wing than the bottom. So according to Bernoulli's principle, the air pressure above the surface, that is the upper surface, decreases below the atmospheric pressure, and that on the lower surface which increases above the atmospheric pressure. So this difference in the pressure which provides an uplift, the upward lift, which we can call it as dynamic lift. So in this principle only it is working. So the aerofoil, or how on the basis of the Bernoulli's principle, it is lift on an aircraft wing. Yes students, so far we have learnt about the Torricelli's law. By using the Torricelli's law, how we have measured the overflow of a liquid, that is outflow of a liquid, and the Venturimeter or flow meter derivation, that is equation of continuity, through equation of continuity, and with the help of Bernoulli's principle we have learned, and some examples of the application of Bernoulli's theorem, that is atomizer, how the spray is working of the spray, aerofoil, that is aero lift, dynamic lift we have studied, and the spinning ball, how the velocity is varying in the spinning ball. Like a different example we have studied for the application of Bernoulli's theorem. Thank you students.